So we've reached the end of the course, and in this video, I'm going to give a little summary of what the course has been about. So this is my version of a course summary, of the stuff that we've covered in this course. So the first thing to say is congratulations. This content is genuinely kind of tough, right? Like this is there's a lot to grasp in this course. There's a lot of ideas in it. There's a lot of multivariate calculus. We pull stuff from all over the place, and we've learned a lot. So you've all done really well just by getting to this stage. And I have appreciated all of the interactions that I've had with you genuinely. Like this is an unusual format in which to teach a course, and it's been great sharing this stuff with you. So thank you. We started off the course with this picture of where different forms of optimization sit. And at the end of the course, it's good to circle back to it and see where where the courses fit in this. So we didn't really talk much about linear programming. That's sort of the domain of optimization and operations research, a different course. We talked a lot about quadratic optimization, and we spent most of the course talking about convex optimization. So most of the time we were on looking at simple sort of convex domains or on intervals, but not all the time. So you've got a feeling of where the different parts of the course sit now in this Venn diagram of supersets of different types of optimization. I prepared another little diagram showing where we've come from and sort of summarizing the different chunks of the course. So when we think about optimization, the first thing that I think about is splitting it into convex versus non-convex optimization. So to sort of start at the beginning and at the end, I mean, maybe the first thing I'll say about this is that the size of these boxes is just designed so that I can fit text on them. Of course, much more of the world is non-convex than is convex optimization. So really the yellow box there should be much larger than the green box. But this is the proportion of time that we spent on each of these topics in the course. So to start at the end and at the beginning, with non-convex optimization, actually a subtle point that it's good to bring out now is that actually the 1D methods that we talked about right at the start of the course, so our dichotomous and our golden section searches in particular, they were actually non-convex optimization methods, right? All that we demanded about functions there, about cost functions, was that they're unimodal, so not necessarily convex functions. So right at the start of the course, we were actually talking about potentially non-convex optimization. And the Newton's method just requires differentiable functions as well to do optimization. So there were actually no assumptions about non-convex optimization. That was something we didn't really emphasize at that point of the course, but coming back now and looking at the whole thing, we did one-dimensional non-convex optimization. And then, of course, right at the end of the course, the very last week of the course, talked about non-convex optimization more generally at a very high level. So the notes sort of talked about simulated annealing, which is a stochastic method for optimizing non-convex functions, where the general idea is that you add some randomness, so you allow yourself to go uphill with some probability such that you can get out of local minima. We also introduced this idea of genetic algorithms, which is a very, very cool modern algorithm that's based on the ideas of evolution and genetic selection. And you should know that that's just two out of many, many more non-convex optimization algorithms. So that's just a little taste of a much broader world of modern optimization that's out there. A characteristic of all of these, or particularly of the genetic algorithms, is that they're these general ideas that are inspired from other places in the world, but we can't prove anything, a lot of the time. So the nice thing about convex optimization is the convex assumption allows us to do a lot of mathematics. So, these non-convex algorithms, a general feature of them is that we cannot prove much, right? So there are lots of parameters to tune. We can have a play with these things. Sometimes they work very well, but we can't do mathematical proofs like we like to do. And so that's why we spent most of the course talking about convex optimization. We talked about convex multivariate optimization. So what's the next breakdown of convex optimization? Well, the obvious thing is to break it into unconstrained and constrained. We did a chapter on both of these. So we started off by talking about unconstrained optimization because that's easier in some sense. And we started off by introducing the steepest descent method, which sort of works the way that you might expect. It does what it says on the tin. You head downhill in the steepest direction that you can. So as long as you can calculate the gradient of your cost function, you head down, in the direction of the negative gradient, the steepest direction all the time. We found that had some issues. That as you got close to the minimum, you might converge very, very slowly. So we talked about if there's a way to speed that up, to get to the minimum in a finite number of steps. And if we restricted ourselves to quadratics, then we could derive this beautiful conjugate gradient method, which would get us there in n steps, where n is the dimension of the problem that we're attacking. And that was built on this beautiful idea of conjugate gradients. The Fletcher-Reeves algorithm, that was really just conjugate gradient again, and the big idea in that was just you approximate by quadratics. So a very simple extension of the conjugate gradient method. And we talked a bit about the stochastic gradient descent method, which is limited to certain types of convex functions where you have sums of convex functions. But the big power of that was really applicable for big data problems. So we had lots of terms in your sum. The stochastic gradient descent method, even though it never converges in the sense that we know about in sort of deterministic schemes or in the sense of a limit, it works really well in big data problems. So a comment here is that in terms of mathematics and proofs of these things, there were only a couple of tools in our tool bag. Most of the proofs that we did of everything in this part of the course, we essentially assumed that functions could be approximated by Taylor series. That was our big hammer. And we also used this convex assumption. So, whenever we had a convexity assumption or quadratics, we used those assumptions all the time. We could prove lots of things about all of these methods just by using Taylor series and the assumptions, the definition of convex functions. So that was unconstrained optimization. And then we said, well, what if we want to not converge to the global minimum, but we have some region, some constraints which define some region in which we're allowed to have feasible solutions. And so, the first idea there was if we have constraints that are equality constraints, so if we're on some sort of boundary of some region, then we use a Lagrange multiplier method. Then the big new idea in this course was how to generalize those Lagrange multiplier methods to the KKT conditions, right? So the KKT conditions allow us, instead of looking at equality constraints, so being on the boundary of some region, when we can have solutions that are within the region as well. So they're defined by inequalities. And really KKT was just a generalization of Lagrange multipliers. We discovered that there was this problem though, that as soon as I have lots of constraints, I get a combinatorial explosion of pairs of constraints, combinations of constraints that I have to check for where the minimum is. And so we needed an algorithm to navigate through that. And so that's why we introduced the gradient projection algorithm, where the idea was to see, is my minimum inside my region? No, if not, it's going to be somewhere on the boundary. So move to the boundary and then navigate around the boundary, heading downhill, so that we get to the solution more efficiently. And everything in this part of the course, we essentially proved by using this idea of convex cones, and that the idea that at the minimizer, the gradient has to point into the convex cone, otherwise there can't be a minimizer. And we derived our gradient projection algorithm based on that. Again, we just use Taylor series again, the definition of convex functions and Lagrange multipliers. And that's it. That's the course. So let's delve in a tiny bit more to each of these topics. So, going back to chapter 2, where we talked about the 1D search methods, we started with the dichotomous search. So the big idea there was that we assumed unimodal functions, and that's all, nothing else. It didn't even need to be differentiable. But these were bounded search problems. So we started off knowing that the minimizer was going to be within some interval, and then we narrowed that down. That took 2n+1 function evaluations, where it's the number of steps that I take. So we thought, well, what if we can reuse some of those function evaluations? And then the best way to do that, the most efficient way to do that, was this golden section search. So we could do less total function evaluations, which makes this a more efficient search scheme. It was the same general principle. Of course, they're both bounded schemes, and the only trick for solving unbounded problems was to try and convert it into a bounded problem, was to find a interval over which I was sure I had my minimizer. And that was this geometric search idea. So essentially, the method for unbounded problems in 1D was to convert them into bounded problems through a geometric search. And then, we're legally required by the laws of mathematics to talk about Newton's method whenever we teach a course on optimization, because it's the jewel in the crown of all of these methods. So it's an unbounded search method where you need differentiable functions, right? Because you need to evaluate derivatives of functions, but really you're just doing a Taylor series expansion of a function, and then Newton's method drops right out. And beautiful thing about Newton's method has this order n squared convergence. So it has this, what we call, this quadratic convergence. So a converger is actually very, very fast. And so that's why it gets used all the time, including in strange places like computer games, as we talked about. Next chapter, chapter 3, we talked about unconstrained methods. So our steepest descent method, was a very simple idea. You head downhill in the steepest direction. We could do some examples of that. It's a reliable method, but the problem is that the convergence can be slow when the function is not very steep. So to get around that, that was the conjugate gradient method. So you introduce the idea of a conjugate direction. It's limited to quadratic functions, but it converges in only n steps. So that was at most n steps. So it's a very, very efficient method for quadratics. Then what if you don't have a quadratic? Well, you approximate your function by a quadratic, and you call that the Fletcher-Reeves method. Easy. That's essentially it. The different one was the stochastic gradient descent function. So we have sums of convex functions that we're restricted to, but that's still pretty general. Lots of problems in machine learning or in statistics have cost functions of that form. So it doesn't converge to a set value. It sort of has some distribution, some variance in our estimates. But because as we talked about, it's wildly more efficient when your sum has got lots of terms in it. So it's a very, very powerful method, and that's why it's used in machine learning these days. Next chapter, we went from unconstrained to constrained. So reviewed Lagrange multipliers, where we have differentiable functions and equality constraints. And then we generalize that to the KKT condition, which is really just a generalization of Lagrange multipliers. There's lots of math there, but that's the central idea. The problem, as I said before, is this combinatorial explosion of constraints that we need to check for where the minimizer is. So we need an algorithm to get around that, and that was the gradient projection algorithm. So we limited ourselves to linear constraints there, just to make the math easier. But we ended up with an algorithm that's sort of like reminiscent of the simplex method, right? So you move around the boundary in a downhill direction. And it stops us having to exhaustively check all of these constraint combinations, which means we can now do high dimensional constrained optimization, which is very, very useful in this modern setting. So that's almost it. We had this one other little review of non-convex, couple of ideas in non-convex optimization. The big idea in that chapter, in that last week, is that most things in the world, most cost functions aren't necessarily convex. There's lots of functions I can write down that are non-convex function. And, there's this generic problem in all of these methods. That's what if I get stuck in a local minima? Right, so what if I have a very complicated function, or I get stuck somewhere in a local minima? How do I get out of that? A couple of different ideas. So either you can accept moving uphill with some probability, and that was the idea in simulated annealing. And I should say that actually gets you into a really, really rich world of what we call Markov chain Monte Carlo methods. And so that's a huge literature in the optimization stochastic statistics field that we barely touched on. But I can commend to you doing some other courses on computation Bayesian statistics, or coming back in honours to talk about. those things some more, because there's a huge literature there. It's a really cool area of optimization, actually. The other thing that we sort of mentioned was these genetic algorithms. And so they were modeled, the idea there is that you have some population of potential solutions. You look at the fitness of all of those solutions after you've encoded those solutions in some vector, and you combine these things, you evolve them together. You genetically mix these solutions so that you evolve new solutions. And that's a very cool idea, and it can work very well. And our completely general cost functions are allowed, but there are lots of parameters to tune, and I can't prove things. So that's the limitation there with that. Great thing to explore, and you can do lots of fun things with it though. And that's it. So that's this is the last slide though. Just that's the summary of the course. Yeah, I mean, it fits into this sort of picture. And if if you get all the bits in that, then that's all there is in the course. So I hope that's a useful overview. Yeah, it gives you a good picture of the really long way that we've covered in this course. So well done.